In episode 87, titled DDoS and SYN Floods, Recognition Patterns and Mitigations, the focus is on denial attacks as availability threats that demand layered defenses rather than a single magic control. Availability is a security property, and denial attacks are one of the most direct ways an adversary can harm a business without ever stealing data. The exam framing typically emphasizes recognition patterns and practical mitigation categories because the first win is knowing what you are seeing and what levers you can reasonably pull. When you approach denial as an operational security problem, you naturally start thinking about where to absorb load, where to shed load, and how to protect the stateful parts of the system that cannot scale infinitely. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A distributed denial of service, commonly called a DDoS after first mention, is best understood as many sources generating traffic that overwhelms bandwidth, infrastructure, or application capacity. The distributed aspect matters because it complicates simple blocking strategies, since requests can come from thousands of addresses and networks that look superficially legitimate. Some DDoS attacks focus on raw volume, aiming to saturate links or overwhelm edge devices, while others focus on exhausting service capacity by forcing expensive processing. The key exam-friendly idea is that the attacker's goal is not elegance, but asymmetry, where the attacker spends little effort per packet while the defender pays in bandwidth, compute, or operational time. Understanding whether the stress is on bandwidth, compute, or a specific dependency is how you choose the right mitigation layer. A synchronization flood, commonly called a SYN flood after first mention, targets the connection establishment process by exhausting connection state on servers, load balancers, or security devices. In the transmission control protocol, a connection begins with a handshake, and the SYN packet is the opening request that causes the receiver to allocate resources while waiting for the handshake to complete. When an attacker sends large numbers of SYN packets without completing the handshake, the target accumulates half-open connections and eventually runs out of state capacity, which can prevent legitimate users from connecting. This is why SYN floods are often described as state exhaustion attacks, because the bottleneck is not bandwidth alone, but the finite tracking structures inside stateful systems. The exam typically wants you to recognize that state is a scarce resource, and that protecting state is a different problem than simply adding more bandwidth. The symptoms of denial attacks often present as a user experience problem first, even when dashboards still show systems up. High latency becomes visible when queues build because requests wait longer to be processed even if they eventually succeed. Timeouts follow when requests exceed client or proxy time limits, and timeouts can cascade as retries amplify load and create a feedback loop that makes the attack more effective. Rising error rates appear in application telemetry and edge logs, often showing a shift from occasional errors to sustained failures across many endpoints at once. The important point is that symptoms are patterns, not single signals, and the exam expects you to connect latency, timeouts, and errors to overload dynamics rather than assuming a random bug. One of the most effective responses to large denial attacks is upstream filtering and scrubbing, because the best place to absorb massive traffic is before it reaches your constrained links and stateful systems. Scrubbing refers to diverting traffic to a provider or service that can separate malicious patterns from legitimate requests at scale, returning cleaned traffic to your environment. Upstream filtering can include network-level controls at internet service providers, edge providers, or cloud-native protection layers that drop obvious attack traffic without consuming your core capacity. This matters because if the attack traffic reaches your perimeter, you may already be paying the price in bandwidth and device load, which limits your options. A layered defense mindset treats upstream absorption as the first major lever for volume attacks because it protects the downstream components that are hardest to scale quickly. Rate limiting and connection limits are the practical tools that protect stateful systems because they control how much work a system will accept in a given window and how much state it will allocate to any given source or flow. Rate limiting can be applied at multiple layers, such as at an edge proxy, load balancer, or application gateway, and it helps prevent request floods from turning into compute starvation. Connection limits focus more directly on state, restricting the number of concurrent connections or incomplete handshakes to prevent tracking structures from being exhausted. These controls are not about stopping all malicious traffic, but about preserving enough capacity for legitimate users to get through, which is the core availability goal. The exam often frames these as mitigations that buy time and stability, while upstream protections and incident processes catch up to the attack. To see how this plays out, imagine a web service that becomes unreachable during a sudden traffic spike that begins without warning and overwhelms normal peak planning assumptions. At first, monitoring shows response times climbing and a growing backlog, and then user reports shift from slow to cannot load, which maps directly to the latency and timeout progression. If the service is behind a load balancer, you may see connection counts rising rapidly, with many incomplete handshakes if a SYN flood is involved, or with sustained request volume if it is an application layer flood. The critical operational question is whether the bottleneck is bandwidth to the environment, state on the perimeter and load balancer, or compute and dependency saturation inside the service. When you can answer that question, you can choose whether upstream scrubbing, tighter connection limits, or application-level shedding will do the most good first. A frequent pitfall is scaling blindly during an attack because auto-scaling and rapid capacity increases can drive costs up dramatically without restoring availability. If the attack is saturating bandwidth, adding more application instances does not fix the choke point, and you simply pay for more compute that cannot be reached reliably. If the attack is state exhaustion at the load balancer or firewall, scaling application backends may still not help because legitimate connections cannot be established in the first place. Blind scaling can also make detection harder because normal baselines are disrupted and telemetry becomes noisy, which slows correct diagnosis. The exam angle here is that scaling is a tool, not a strategy, and you should scale only when you have reason to believe the constraint is within the layer you are scaling. Another pitfall is blocking whole regions or large address ranges in a panic because that can break legitimate users and cause business damage that rivals the attack itself. Regional blocking is tempting when an attack seems concentrated, but distributed attacks often include spoofed or widely dispersed sources, and crude blocking can be both ineffective and overly destructive. Legitimate traffic frequently originates from content delivery networks, mobile carriers, and cloud providers that share address space across many customers, so broad blocks can create false positives at scale. The operational risk is that you create a self-inflicted denial condition that persists after the attacker moves on because undoing broad blocks and validating recovery takes time. The exam generally rewards more nuanced approaches, like targeted filtering based on behavior, combined with upstream scrubbing and rate controls, rather than blunt geographic denial. Quick wins usually center on putting strong edge protection in place before you need it, and tuning thresholds so controls activate in a measured, predictable way. A content delivery network, commonly called a CDN after first mention, can absorb large volumes and keep static and cacheable content available even when origin services are stressed. Edge protection services can also provide request filtering, bot mitigation, and challenge mechanisms that reduce the effectiveness of application layer floods without requiring origin changes during an incident. Threshold tuning matters because default settings are rarely aligned to your traffic patterns, and you want protections that trigger on real anomalies rather than normal peaks. When these quick wins are in place, the response moves from improvisation to execution, which is exactly what availability defenses need under pressure. Monitoring cues are the early warning and classification signals that help you distinguish between normal growth, flash crowds, and hostile traffic patterns. Sudden connection growth is a classic signal, especially when the ratio of incomplete handshakes rises or when connection durations become abnormally short, which can indicate state pressure. Abnormal patterns can include sharp shifts in request paths, unusual concentration on expensive endpoints, odd user agent distributions, or repeated requests that ignore normal session behavior. Traffic that is distributed across many sources but synchronized in timing often looks different from organic user behavior, which tends to be bursty but not perfectly aligned. The exam expects you to think in terms of patterns and deltas from baselines, because recognizing what is abnormal depends on knowing what normal looks like for connection counts, error rates, and request mix. A useful way to keep the concepts organized is a memory anchor that separates volume problems from state problems while tying them to response levers and observable symptoms. Volume refers to overwhelming bandwidth or edge capacity, and it often pushes you toward upstream absorption and scrubbing because the goal is to keep bulk traffic away from constrained links. State refers to exhausting connection tracking and session handling, and it pushes you toward connection limits, SYN protections, and defensive behaviors that reduce state allocation to suspicious flows. Symptoms are the user-visible and telemetry-visible manifestations like latency, timeouts, and rising errors, which help you decide which class you are dealing with. Upstream and limits then become the two major control families, where upstream handles scale and limits preserve critical state, and this anchor stays aligned with how the exam tends to categorize mitigations. When you are asked to choose mitigations for bandwidth exhaustion versus state exhaustion, the most important skill is matching the mitigation to the constrained resource rather than matching it to the most familiar tool. For bandwidth exhaustion, upstream filtering, scrubbing, and edge absorption are usually the most effective categories because they reduce traffic before it hits your links and devices. For state exhaustion, controls that reduce state allocation, like SYN handling protections, connection caps, and rate controls at the edge, often matter more than raw bandwidth capacity. In both cases, layered defenses matter because an attacker can shift techniques, and a response that only covers one layer can be bypassed by changing the pressure point. The exam is testing whether you can reason from symptom to constrained resource to mitigation class, which is the operational way to think about denial attacks. The layered defense story is also about avoiding false confidence, because a single mitigation can create the illusion of safety while leaving an adjacent weakness exposed. If you rely only on rate limiting, a large enough volume attack can still saturate links before rate limiting even sees the traffic. If you rely only on scrubbing, A state exhaustion attack that looks like normal connection attempts can still pressure a poorly configured load balancer if state protections are weak. If you rely only on scaling, an attack that targets a shared dependency, like a database or an identity layer, can still knock the service down while compute grows uselessly. Layering means each control family covers the failure mode of another, and it also means your monitoring can confirm whether the attack is shifting. That is the kind of defensive reasoning the exam rewards, because it reflects how real systems fail under adversarial pressure. Episode 87 wraps with a simple conclusion. Denial attacks are availability problems that reveal where your architecture is brittle, and the best response is to recognize patterns quickly and apply layered mitigations that protect both bandwidth and state. Distributed denial of service attacks stress scale, while synchronization floods stress state, and both create recognizable symptoms in latency, timeouts, and error rates when they begin to bite. The mitigation mapping drill is to take a described disruption, decide whether the primary constraint is volume or state, and then map upstream protections and local limits to the layers most likely to help first. When you can narrate that mapping clearly, you show the exam-level skill of turning observed behavior into practical defense choices without chasing distractions. With that skill, denial stops being mysterious and becomes a managed risk that your architecture and operations are prepared to absorb. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.